Okay, my name is Ryan Berg, and here's my video for the Torsion test lab. This lab was very interesting as we got to test the strength of 3 different materials using a torsion testing machine. The way the machine worked is we put a specimen, which was made of a certain metal, into the machine and then twisted it until it deformed or broke. Using software made for the machine, we were able to collect data about the material while it was being twisted. The data we collected includes polar moment of area, surface shear stress, surface shear strain, the angle at which the material was rotated, torque, and peak torque, all relative to time. I will go over the data later in the video, but I'll start by showing you the setup of the machine. It is my voice in this first video, so I'm not going to speak over it. I'll just let my original commentary explain what is happening. Okay, this is video number 1 showing the setup. Here we have the base, the specimen inside, the digital meters right here, all hooked up and ready to go. And here we have the versatile data acquisition system. And this is our software getting ready to run. Alright, that's that. Now I'm going to take you through the 3 materials that we tested. The first material was TR1050, which I will open up now. Okay, here is the video. TR1050 is made of cast iron. I cut most of the video out, but we ended up twisting it for about 2 minutes and 30 seconds until it snapped at 65.28 degrees of rotation. As you can see there, it has snapped. Okay, now I'm going to show you the picture. Alright. Here's the picture of the end result. You can see the point of failure was off to the side instead of in the middle. Okay. Now the next video is of TR1021, which I will open up now. Now we ended up rotating this thing for a little over 4 minutes, and we got it twisted all the way to 600 degrees, and it still didn't snap. It ended up just twisting further and further like a candy cane. TR1021 is made up of 0.4% carbon steel. So that's the end of that video. You can see it's kind of candy caned all the way around there. Alright, here's a picture. TR1021, the final result. You can see it's still intact, but it's very weakened from rotating so much. Okay, the final material is TR1040, and I will open up this video now. Alright, so there it is. TR1040 is brass. This material ended up rotating for a little over 3 minutes and made it all the way to 608.86 degrees before snapping. And there it is, point of failure. Okay. Here's the picture. Okay, you can see just like TR1050 that it failed at the side instead of in the middle. I think the reason these 2 materials failed at the side was because they were stationary at that point. So when it began to twist, that was the main point of rotation. Okay, now let's go over the data. Let's open this file up right here. All right. All right, now here's the beginning, data series 1. Let's go down to data series 2. Okay, data series 2 corresponds to TR 1050. Now let's scroll over right here. You can see that it had a length of 100 millimeters and it has a diameter of 6.10 millimeters. You can see the categories here that I listed earlier. You have polar moment of area, surface shear stress, shear strain, angle in degrees and radians, torque, peak torque, and the material listed over there. And it's all relative to time. As you scroll down, the time increases and you get to see the data at all those points in time. So let's go down to the bottom. Okay. Right here is the moment that it snapped. You can see it snapped at 65.28 degrees as the shear stress and torque dropped suddenly. You can see the final shear stress that it was able to withstand was 387.3 meganewtons per meters squared. And the final torque was 17.26 newton meters. Now, if we scroll down to data series 4, here we go, data series 4. We can see the data for TR 1021, which also had a length of 100 millimeters and a diameter of 6.05 millimeters. You can see that right here. Okay. Now, it also has a polar moment of area of 131.53, and that's consistent all the way down. Okay, so if we scroll down to the bottom of 1021, we can see that there was no moment of failure and that we stopped the rotation at 600 degrees. Let's go all the way down to the bottom here. It's a lot of time that lapsed. Okay. All right, here we go. Here's the bottom. All right, we really probably should have spun this one longer, but we figured it would rotate for a really long time and not fail because it was so ductile. It has a final shear stress of 544.4 and a final torque of 23.67. But what's interesting about this data is that if we scroll back up a little bit to 210 seconds. Let's see. All right, we'll find that the shear stress and the torque don't really get higher. They just kind of fluctuate at about 555 and 24 respectively until they drop a little bit towards the end. Now, let's take a look at that. See, you can see the torque and the shear stress just kind of fluctuating, not really getting higher. Just kind of stay the same until we get to the end, and then it just drops a little bit. Now, this is representative of the material's ductility. It means the material got sort of gummy after about 540 degrees of rotation. Okay, so the last data series here is data series 5. And this represents TR 1040. It has a length of 100 millimeters and a diameter of 6.05, just like the last one. Let's go over here, as you can see. Alright, it has a consistent polar moment area of 131.53. If we scroll to the bottom here, we can see its point of failure is at 608.86. Let's see. Yep, right there. 608.86 degrees. And it was able to withstand 397 meganewtons per meter squared of shear stress and 17.26 newton meters of torque. Okay. That's it for the data and the experiment. These three materials were interesting to analyze, as they all had different properties and produced different results. The cast iron snapped quickly compared to the brass, but they both had a distinct moment of failure, while the carbon steel rotated for a long time before getting weakened, but didn't break, as it is a more ductile material. And that is all. Thank you.